The Joe Rogan Experience.
And the other thing is, I don't know if you're familiar with this, but there's now a connection between quantum computing and black holes. Yeah.
What's that connection?
It's a weird one. So
it's all weird.
Well, this is like weird squared or something. But work over the last 20 years has established that when you have a black hole, actually even more general systems, but talk about a black hole, there's an alternate description of a black hole in terms of what's known as the holographic description. It's as if there's a two-dimensional world that surrounds any given three-dimensional world that has exactly the same physics as the three-dimensional world that we're familiar with, and yet it describes it in a completely different language. So a black hole gravity is obviously essential. That's how a black hole forms. But in this dictionary that physicists have developed, there's a description of a black hole that doesn't involve gravity, only involves quantum mechanics. And the beautiful thing is the quantum processes in that quantum world mimic the kinds of processes that people have been developing for quantum computing, quantum error correction code. And there's a dictionary that people have proposed for that quantum language on the holographic boundary with physics in the interior. And the dictionary shows that the quantum error correcting code may be the reason why space-time itself holds together. So there's this bizarre way in which everything that we know about in the world around us has a translated dictionary version in a different world that lacks gravity but has quantum mechanics. And so people are using some of the insights from quantum computing to understand questions about black holes and space-time.
So
is that strange?
That's so strange. So as quantum computing expands, much like as computing expands, if you go back to the early NASA computers that filled up a whole room, we can extrapolate that as we get better at this, and you look 50 years down the line from now, quantum computing will be the standard. It will be the norm.
Yep.
And it would probably radically alter our understanding of everything.
Including black holes.
Including black holes.
That's right. So there's a real possibility that the language that we use for space-time and black holes may bear a profound imprint of the language that we are developing to understand quantum computing, quantum computers.
I was just reading some article about black holes roaming through the universe, and that some of them, they're detached from galaxies, right?
They can be. I mean, oftentimes people think about black holes as these gargantuan structures that form from collapsed stars. There's a big one in the center of our Milky Way galaxy, weighs 4 million times out of the sun. The photograph of a black hole in the galaxy M87 that got the world excited a couple of years back, 55 million light years away, billions of times the mass of the sun. But the reality is anything, if you compress it enough, becomes a black hole. If you take an orange and you squash an orange down sufficiently small, according to Einstein, it becomes a black hole. So these things don't have to be gargantuan. The flip side of it is we also typically have an intuition that black holes are really dense, right? That's usually the way we think about them. But if you make something sufficiently large, regardless of how low its density is, it will also become a black hole. So you can make a black hole out of air by just having enough air. If you have enough air, sufficiently large sphere of air, it would become a black hole too, with the density of air. So all the intuitions that we typically have about black holes, that they have to be dense and they have to be gargantuan, not right.
So black holes are just a part of the elemental structure of reality itself.
Yeah, when you look at Einstein's equations, right in his mathematics, there's a little formula that you can see where it says if you have any mass m, whatever mass you want, and you squeeze it into a radius r that's less than 2 times Newton's constant 2g times m divided by c squared, speed of light squared. A formula. Details don't matter. But you take any mass, if the radius within which that mass sits is less than 2gm over c squared, it is a black hole. Period. End of story, according to Einstein. Now, Einstein left out quantum mechanics. Weirdly, right? Because his Nobel Prize was for quantum mechanics. It was for a paper he wrote in 1905 about the photoelectric effect. But he never really believed that quantum mechanics was the true description of the world. And when he was developing the general theory of relativity, he was just thinking about gravity and not quantum mechanics. Stephen Hawking came along in 1974 and started to inject quantum mechanics into our understanding of things like black holes. And that's where Hawking proved that black holes are not completely black. He showed that black holes allow a certain amount of radiation to leak out of their surface, leak out of the event horizon, or leak out from just beyond the edge of the event horizon. And so, yes, when you think about black holes, as far as we can tell, they are a fundamental quality of the world, but you have to include quantum physics to truly understand them, and that's the cutting edge of what's happening right now.
So they're a fundamental quality of the world, but they're also in the center of every galaxy.
It seems to be the case. The Sloan Digital Sky Survey did a wonderful study of a vast number of galaxies. And I've seen these wonderful images where they put like a little red circle around all those galaxies that have a black hole in their center. And there are red circles all over that imagery. So it seems to be a ubiquitous quality that black holes are at the center of galaxies. And those are typically gargantuan black holes, millions or billions of times the mass of the sun.
Do we know why they exist at the center of a galaxy?
You know, there's still a lot of uncertainty about galactic formation. You know, some have suggested that early stars, which were quite large compared to more modern stars, when they exhausted their nuclear fuel and they collapsed in on each other, they created black holes that were large, and then they continued to suck in more material from the environment, and they grew larger and larger still. So that's sort of one rough way that people think about how these massive, enormous black holes may have formed, but it's uncertain. LIGO, you know, this Laser Interferometer Gravitational Wave Observatory, gravitational waves, it took headlines a few years ago when it detected the first ripples in the fabric of space. It detected them from two black holes that were 1.4 billion light years away, like 1.4 billion years ago, rotating around each other, going near the speed of light, slamming into each other, creating a tidal wave in the fabric of space that rippled outward at the speed of light. Part of it raced toward planet Earth. There wasn't anybody on planet Earth to see it at that moment, but it had 1.4 billion year journey to traverse. It raced toward planet Earth. When it's about 100,000 light years away, grazes the Milky Way galaxy, it continues to race toward Earth. When it's 100 light years away, a guy named Albert Einstein writes down equations that suggest there could be these gravitational waves, unknown that one is already racing toward the planet, right? And it continues to race onward. 2 light days. It's 2 light days away when they turn on the newly refined version of the LIGO detector. And 2 days later, that wave rolls by planet Earth, shakes the 2 detectors, one in Louisiana, the other in Washington State, giving us the first direct detection of ripples in the fabric of space and establishing that the story that I told you is true.
Wow.
You know, so these things are real. They're out there.
That is wild.
And before the direct radio telescopic imagery from the Event Horizon Telescope of the black hole in M87, that ripple in the fabric of space was the most direct evidence that black holes are real, because when you took the way that the machine in Louisiana and Washington, it twitched for just, you know, a tiny fraction of a second, when you figured out using supercomputers what the cause of the wave must have been, you are led to 2 black holes that are 28 and 31 times the mass of the sun, or 36 times the mass of the sun, numbers of that sort, and that was the only explanation for the data. And so there's this beautiful indirect proof that these stellar-sized black holes are actually out there. And then, of course, we take a photograph of one in a nearby galaxy.
So do we know why black holes would collide with each other? Are they attracted to each other because of their mass?
It's a good question, yeah. So certainly that is part of it. So binary star systems are not uncommon. They're fairly common, where 2 stars will be orbiting around each other. If those 2 stars exhaust their nuclear fuel, they can each collapse to a black hole. So that's one possibility. Or it could be a black hole's wandering through and captures another black hole. It's a possibility too. I mean, go ahead and ask your question, but there's one point I want to make as well, which is...
Wasn't that... Good, please go.
Yeah, well, it was just that many people have in mind that black holes sort of reach out and grab everything in.
Yeah.
But a black hole of mass m, a black hole whose mass is the same as the sun, has the same gravitational pull as the sun. It's not, it doesn't pull any harder than the sun. It's just that you can get closer to it because it's so small and therefore you can experience the gravity more strongly. But, a brick of mass M and a black hole of mass M, they exert the same gravitational pull.
Okay, so we have this misconception that black holes are always these supermassive objects that have incredible amounts of gravity,
Yeah.
and they're sucking in planets and stars and
Right.
churning them up. Because we're thinking of massive black holes, like the supermassive black holes are at the center of the galaxy,
Yeah.
which is like, what, 1/2 of 1% of the mass of the galaxy?
Well, let's see. So if our galaxy has, say, 100 billion suns, and that guy is about 4 million times the mass of the sun, you're talking about, a thousandth or something of that sort.
Isn't that
Yeah.
crazy when you
Yeah.
say that 100 billion suns, and you have to wrap your head around the idea of 100 billion stars, and that's just our little puny little galaxy.
Well, that's a thing. And there
Isn't that
are at
crazy?
least 100 billion galaxies.
At least.
And this is just in the observable universe. I mean, do you know if you take your thumb and you put your thumb on a nice clear night and you block out a thumbnail worth of the sky, you're blocking out about 10 million galaxies.
It's so crazy. It's so crazy because those numbers, I hear you say those numbers, I can repeat those numbers, but I don't think I'm really internalizing them.
You can't, because they're so non-human scale, right?
Yeah.
We've just never experienced anything like that at all. And it could be that it's infinite. Space could go on infinitely far. It could be that the galaxies continue onward infinitely far, and therefore the numbers we're talking about could be minuscule on the scale of the fullness of reality.
Catch new episodes of the Joe Rogan Experience for free only on Spotify. Watch back catalog JRE videos on Spotify, including clips. Easily, seamlessly switch between video and audio experience. On Spotify, you can listen to the JRE in the background while using other apps and can download episodes to save on data cost, all for free. Spotify is absolutely free. You don't have to have a premium account to watch new JRE episodes. You just need to search for the JRE on your Spotify app. Go to Spotify now to get this full episode of the Joe Rogan Experience.